Good morning, geographers. So we've got the Edexcel A-Level Geography Paper 1 coming up on the 12th of May. And your folder is overflowing with case studies that you just can't simply commit to your memory. Stop panicking. Over the next 40 minutes, what I'm going to try to do is give you as succinct as possible overviews of all the essential AO1 that you need to do well in that big 40-mark section within that Paper 1. From the collapsing cliffs of Holderness to the management strategies along the Holderness coastline and in places like Kenya, and in places like Haysborough, Blackwater Estuary, Undercliff in the Isle of Wight. This isn't just a summary, it's your AO1 Bible for those 8 and 20 markers where examiners are continually commenting that you need to include more case study detail if you are looking to achieve those higher level marks. So we're starting on the south coast at the Isle of Purbeck, the only place where you can see 2 completely different coastlines in one afternoon. Let's get cracking. So the Isle of Purbeck in Dorset shows us how geology dictates the shape of a coastline. Let's look at the east coast first. This is a discordant coastline. So the sea eats away at that soft clay layer, carving out the deep curve of Swanage Bay, while the resistant chalk stands firm, creating huge headlands like the Foreland, in which we will see the classic stack stump arrangement, which we'll come back onto later when we do wave erosion. Now just travel a few miles south and everything changes. This is where the rock layers are parallel to the shore, creating a natural outer resistant wall of Portland limestone. So for thousands of years, this outer wall stood firm, but the sea found a weakness, exploited it. This can be a fault or a fracture or a joint or a small gap, and it found a way to breach that limestone layer. And behind that wall, as we've already seen, sits the weaker, less resistant Wealden clay. The waves enter this breach, and because of the process of wave refraction, these waves then start to mushroom out, rapidly hollowing out that clay layer behind it, increasing rates of lateral erosion more than anything. But then because of that wave energy dissipation, we get deposition at the back, and that's where we form that beach layer across the back of the cove. And this creates that near perfect circular Lulworth Cove. So in terms of that revision checklist, discordant, perpendicular creates headland and bays. Concordant, parallel creates coves. Now what we've just covered there comes under the bracket of geological structure, under geology. Now, you can't talk about geology without talking about the other side as well. Lithology is, what are these rocks made of? And a lot of the time, you relate lithologies to the rates of recession. And we can look at 3 distinct sites to prove this. Holderness is the most obvious example to look at when we're considering unconsolidated lithologies. Now, unconsolidated lithologies haven't been through that process of lithification, which is like the compression and compaction into a rock layer. So first, if we consider the Holderness coastline in Yorkshire, this is the fastest eroding coastline in Europe. But why? Because we've got an unconsolidated glacial boulder clay, which was deposited during the last ice age. It's got no internal strength because the individual particles are simply held together by friction. So when it gets wet, it loses all its cohesion, increasing the likelihood of rotational slumping, which we'll come back to in 2b.6. But it's also very easily worn away by hydraulic action as well. Not the hydraulic action where you've got the compression of air into weaknesses, it's more the hydraulic action which is just the physical force of water. The result? Huge slumping and a recession rate of 2 meters plus per year. Next up, we've got the igneous crystalline kind of rocks. And these are at the other extreme, and this is where we can look at Land's End in Cornwall. So this is a granite. So when we talk about crystalline rocks, we're talking about the interlocking crystals that form part of its internal cohesion. These are very strong rocks, very resistant to erosion because these rocks formed from the very slow cooling of magma beneath the surface, which is why they have these strong interlocking crystal bonds. This leaves almost no pore spaces for water to get in, so the chances of these rocks becoming saturated is very low by comparison to the boulder clays of Holderness. And it's also incredibly resistant to erosion, so the force of abrasion, hydraulic action, it's a lot more resistant to those forces. At Land's End, the recession rates are around 0.1 centimeters per year, despite the fact that area of the UK coastline receives some of the highest energy waves during winter across the country. And this is all due to the 4,000 kilometre fetch across the Atlantic Ocean. So it's incredibly resistant and testimony to the fact that lithologies can influence recession rates. Then we have sedimentary, which is almost like our halfway house between the resistance of igneous rocks and the lack of resistance of unconsolidated rocks. The best case studies you can use here is the Glamorgan Heritage Coast. And this is in Wales. It's a Carboniferous limestone. And if you just look at this cliff face, you'll notice there's a number of geological factors that we can potentially focus on. Simply by looking at it, the visible bedding planes are evident. But as well as that, evidence that you can see that it's sedimentary rock also comes in the form of the fact that it's very heavily jointed. And these joints can be very easily exploited by hydraulic action. And so we see an abundance of what we would call microfeatures. Things like caves, blowholes, and narrow inlets where the sea has exploited these weaknesses and led to the creation of these features. We also see quite extensive wave-cut platforms as well. So this is an excellent one to talk about the fact that lithology doesn't only influence recession rates, but it also influences landforms as well. Furthermore, we can bring back in this idea of geological structure when we can think about the angle of the dip of the bedding planes. We can see very clearly that this is a horizontal dip bedding plane, which results in a very vertical cliff profile. So Glamorgan Heritage Coastline is a very versatile case study to bring in all of the geological factors that could possibly influence the development of a coastline. Small pause, just a little reminder of the 2-day masterclass that I'm running on the 9th and 10th of May, which is the weekend before the 12th of May exam. The 2-day masterclass, very different to anything that I've run before. Last year, this 2-day masterclass was attended by over 100 students, and they used it as that final push to just give them the exposure to the core content needed for the Paper 1 module. Here's an example of how it's going to run. So I'll ask you a question, which might be something along the lines of 3 ways that plate boundary can influence the scale of disaster. You go away and you write something for 2 minutes. After that 2 minutes, I'll get some responses on the meeting chat, and I'll fill in the gap on the whiteboard that's normally there. And then we go back, we go forth, we go back, we go forth, and we cover the entire Paper 1 specification, but that way. We keep you engaged. It's an active form of revision, and it means you're not on your own in those final stages of preparation, where sometimes it's the most difficult to realize what on earth can I do with the remaining time that I've got when there's all this content to go through. Okay, so this currently is still on special offer, $14.99 for the 2 days. And remember, on the 1st of May, it will be going up to $24.99. So lock it in now and save yourself a tenner. Okay, back to the video. Okay, and the final part of geology and the way that it can influence the coastlines is looking at the concept of deformation. Sometimes the Earth doesn't just sit there. It gets squeezed by tectonic forces. And there's no better place to see this than at the Lulworth Crumple at Stair Hole. About 30 million years ago, the collision of the African and the Eurasian plates, the same event that built the Alps, sent shockwaves north. And the tectonic pressure compressed layers of limestone, shale, and because these rocks were under immense pressure and heat, they didn't just snap, they became plastic and folded. So if you look at the tight zigzags and folds along the Lulworth Crumple, you'll see anticlines and synclines. So the peaks are the anticlines, the dips are the synclines. So in the exam, you'd describe this as intense folding. And this kind of structure is just a series of, or a collection of weaknesses. And the sea can very easily exploit the hinges, if you like. So the anticlines and the synclines, because of that folding, it creates a number of weaknesses, and these are the areas that are exploited. And so we get the rapid formation of both caves and arches, like the ones that you see here at Stair Hole. So the Lulworth Crumple proves that coastal shape isn't just about erosion. It can also be about tectonic history and in the interaction with geology and wave erosion as well. So if that rock is pre-weakened by folding, if you like, it's half the job done. Then once we're done talking about geologies, particularly unconsolidated geologies, and explaining how they are some of the least resistant coastlines, what we then move on to is almost an evaluation point, if you like, about the fact that unconsolidated geologies could be stabilized by vegetation. And this is where we come on to plant succession. Now, there's 2 types of plant succession that we look at. There's Samosaid plant succession, which is very much the evolution of a sand dune ecosystem. There's also Halosaid plant succession, which is the evolution of a salt marsh ecosystem. two examples that we're going to look at. Formby is one of your best examples for sand dune plant succession. So at Formby Point, we see the classic Samoset model playing out. So it starts on the strand with species like sea rocket, and these are our pioneer species, the ones that can handle high salt exposure, zero shade, not a lot of water, and they trap a tiny little bit of sand, and this is what creates our embryo dunes. These are fragile, but they start that process of changing the environment. Further inland, we then hit those enormous yellow dunes, which then become dominated by what you could probably term as the MVP of sand dune environments, which is marram grass. MVP, by the way, a term utilized in popular sports such as basketball and American football, and it stands for most valuable player. Not only do these long roots bind the sand together, the leaves have very high growth rates, which means that they can trap a lot of sediment and build up that dune environment. But also, when these types of vegetation die, they then increase the amount of dead organic matter in the soils, and that increases the amount of nutrients available for the next species that will then come as part of that next seral stage. And this turns that ecosystem to more like a grey than a yellow. Then finally, we reach the dune slacks where the water table becomes exposed, allowing for mosses and willows to start to cultivate. And then eventually you reach that climax community at Formby, which is a pine woodland. The environment is now stable, nutrient-rich, and sheltered. So remember the sequence, it goes from embryo to yellow to grey to climax. And as long as you know the different types of species at each of those stages, what their function is, and where this all takes place, Formby, you have all the AO1 you need. Then we move on to salt marshes. One of the examples you can use here is the Keyhaven marshes. If sand dunes are about wind in terms of supplying that sediment, salt marshes are about the tides. So in Hampshire, the Keyhaven marshes are a perfect example of this. It's a low energy environment, and these low energy environments are normally created because of the creation of a spit. So in this case, that's Hurst Castle spit. This is where fine silts and muds can settle via flocculation, and they create this halosphere. So the first plants to arrive are the halophytes, and these are the ones that have to survive being totally submerged twice a day. So their roots and their leaves slow down the water, trapping more sediment, and then actually raising the height of the land eventually above the high tide range. Eventually the land becomes so high that it only becomes flooded by those spring tide kind of floods. The salt becomes washed out by rainwater, and the climax community then becomes oak, alder, or ash trees. And this is where the marsh usually then officially becomes terrestrial land. And that's EQ1, all sorted. Okay, then we move on to 2, which is much more process heavy. And we start out with the action of waves and then wave erosion. So most people think a beach is just, well, a beach. But in reality, they are these environments that are constantly adjusting to remain in the dynamic equilibrium within which they exist. They change their shape to handle whatever energy the sea throws at them. So in the summer, what we'll normally see is constructive waves. They're low frequency, they have a strong swash and a weak backwash. So they push sediment up the beach, building a gradual, wide profile with a noticeable ridge at the back called a berm. The beach is growing because of the process of deposition. Come winter, this energy shifts and we have more destructive waves. These are high frequency, weak swash, incredibly strong backwash, and they scour the sand away, scour it away, dragging it offshore. The steep berm disappears and the beach becomes more angled, leading to a very random assortment of sediment sizes. By comparison to your constructive beach, which is where we have larger sediment at the back and smaller sediment at the front. On our winter beaches, that scour then creates an offshore bar. So it's almost as if you get the bar, the berm, the bar, the berm, the bar, the berm. But here's the clever bit. That offshore bar, the bar, actually protects the coast. It causes those big winter waves to break further out to sea, reducing their energy before they hit the cliffs. And this is what's known as a negative feedback loop. And then the beach changes shape almost to protect itself. So if they're breaking further out, they're then more likely to become constructive waves that will push the sediment back up and rebuild the beach. So when the summer builds the berm and the winter builds the offshore bar, we have that constant cycle of sediment exchange. So the winter waves create the bar, and then because that bar's been created, we get the breaking of the waves early, and then we push that sediment back. And it's that constant moving back and forth, which is that transition from a winter to a summer beach. And you can use any beach to suggest that this happens. Then we move on to our landforms of wave erosion. Cliff retreat leaves behind a footprint, and this is a wave-cut platform. And there's no better example than the one at the base of Seven Sisters in East Sussex. So it starts with hydraulic action and it becomes concentrated between the low and the high tide mark. And this carves out a wave-cut notch. As the notch gets deeper, the cliff above becomes unstable because it's been undercut. Eventually, the force of gravity exceeds the internal cohesion of that rock layer and the overhang collapses. And the cliff retreats. What's left behind is this big, flat, rocky bench. But it's not perfectly smooth. It's usually covered in debris and scree, and this can be sort of broken down into smaller pieces via attrition. And then in the limestone areas like Kimmeridge, you will also get corrosion. And this is where the salt water chemically dissolves the rock, and this is where on the wave-cut platform you'll see those grooves and runnels that are evidence of corrosion taking place. But here's the kind of really high-level theory that you then need to bring in. So these platforms don't just grow forever. If you think about it, they will grow. But as they get wider, they will force the waves to break further away from the cliff, meaning that there's a greater expanse of a platform to dissipate that wave energy before it hits the cliff. This again is a negative feedback mechanism, slowing down the rate of erosion the wider the platform gets. So we'll normally see these wave-cut platforms around headlands, that's very common, but also at concordant coastlines where there's that kind of consistent rate of erosion along the coastline. And particularly where we've got a 90-degree angle of swash approach. Where we have discordant coastlines and headlands, we also see the cave arch stack stump formations. Old Harry Rocks in Dorset is the perfect example for this. Is the sequence of events that turned a solid headland into, well, there's a pile of rocks in the sea and an enormous stack, and then there's a stump as well. And like we've already said, it's on a discordant coastline, but in some resistant chalk. This is where we can bring in the very important concept of wave refraction. So when a wave approaches a headland, it won't simply attack the front of the headland. Because of wave refraction, it will also attack the sides. So the sea will then exploit a fault or a joint within the sides of the headland, creating a cave. As this continues with caves on both sides, eventually the waves will break through and they will form an arch, just like in nearby Durdle Door. Marine erosion continues to attack the base, weakening the rock layers above, leading to further collapse of the arch, and then that arch will grow. Then subaerial processes like weathering, carbonation, will weaken the roof further, and eventually the roof becomes too heavy and collapses, and that's when we then get our stack. That's Old Harry. But the sequence doesn't stop there. Hydraulic action and abrasion continue to attack the base, leading to those notches where we will get further collapse from the stack above. And that's then when we get the stump, often visible at low tide. So remember, cave, arch, stack, stump, it's the story of wave refraction at the base and weathering at the top. So you've got to mention both and that they act together if you want to score those high marks. Can't look at EQ2 without looking at the concept of the coastal sediment cell. And this is where we look at stretches of coastline as entire systems. Closed systems to be more precise. Well, theoretically closed systems. The idea with the coastal sediment cell is that there is a theoretically finite amount of sediment, and the sediment just moves around that particular cell. These are often delineated by features like headlands, and then output areas or sink areas like spits. And the idea is that you won't get sediment from another sediment cell entering this sediment cell, but you also won't get sediment from this sediment cell then going into another sediment cell. So the sediment just cycles round. And this is why we say that stretches of coastline exist on the wider scales, not just on beaches, within a dynamic equilibrium. So the case study we're going to look at is Sediment Cell 2, and this is along the Holderness coastline from Flamborough Head, Spurn Point. And we need to think of this as being like a conveyor belt of mud, sand and silt. So we break up the sediment cell into the sources, transfer zones and sinks, because every system needs a source, it needs inputs. So at the northern end we have Flamborough Head. Erosion here in the form of weathering, mass movement, hydraulic action, abrasion, provides the sediment, and so too do the boulder clay Holderness cliffs. And it feeds the cell with roughly 1 million cubic meters of sediment every year. The transfer zones, this is where that process of longshore drift, which we're going to come on to, move sediment along the beaches. So the prevailing winds from the northeast create powerful longshore drift effects that carries material south. And we would call this a very high energy transfer zone or transit corridor. Sediment is constantly on the move and heads towards the Humber estuary. Finally, we hit the sink zone, and this is where energy drops and the sediment is deposited, which has created Spurn Point. A huge 6-kilometre recurved spit, and the spit is literally built from the recycled remains of the cliffs further north. But if you stop erosion at the sink, Spurn Head will reduce in size. If you interfere with the movement of sediment through that sediment cell, like with groins, again, that spit will shrink in size. And this is the idea of the dynamic equilibrium within which the sediment cell exists. And since we've just talked about the sediment cell and Spurn Point, this is the perfect follow-up now to talk about depositional features within our coastal sediment cell. So Spurn Head is our classic spit, and it's the textbook example of what happens when a coastline suddenly changes direction. Now, the change in direction has to be an angle of greater than 30 degrees, and this land turns sharply inward at the Humber estuary. But longshore drift carries on in the same direction, and when it enters deeper water, it loses energy and then deposition takes place. And that load is then dropped, and successive loads that have been dropped have created this large sand and shingle ridge. Have you noticed the hook at the end? That's caused by wave refraction or the occasional secondary winds in a different direction, these being from the southwest, which push sediment back in towards land. Now, behind this protective arm is where we then get calmer waters, and this is where silt is then allowed to settle to form those salt marshes, which brings us back to the halocene that we talked about earlier. But Spurn Head is very fragile. It's in a state of dynamic equilibrium, as we've suggested before. So in 2013, for example, a huge storm surge actually breached this spit, which turned the end into an island at high tide. And this was further exacerbated by the fact that the sediment supply is constantly being interfered with by the groins at Hornsea and Mappleton. So it's a consistent starvation of sediment for this particular spit. So Spurn Head, in terms of a depositional feature, you don't just want to see it as a pile of sand. It is the entire outcome of the movement of sediment throughout that sediment cell. Just a quick one on deposition and those processes of deposition. We need to get our terminology checks in place. So you need to know two technical processes, one gravity settling and two flocculation. Gravity settling is very simple physics. When the velocity of the water or the wind decreases, the energy is no longer high enough to transport that sediment. The heaviest particles like pebbles and sand, they're the ones that drop out first. Now you see this at Chesil Beach. Flocculation, that covers our tiny stuff. So fine clay and silt particles are transported along the river in suspension. And they're so light that technically they could stay suspended forever. Also, when they move along the river, they rub against each other and they become charged. They are charged with the same charge. So the chances of them actually clumping together are very low. If you've ever tried to put two same ends of the magnet together, they just do that. And that's the situation here. But when our silts and clays emerge in the low energy environment, usually behind spits, they lose their charge because of a chemical reaction with the salt water. Then they're able to clump together like this, and when enough of them clump together, they gain significant weight, and then gravity settling can take place. And that's when we get our mudflats, and that's the starting point of our salt marsh. So think about it. Gravity drops the sand, flocculation drops the mud. Okay, back to the rest of the depositional features. So spits are just the beginning. Those of you going for the A's and the A stars, you need that full range of depositional features. So when the sea loses energy, it gets nice and creative with that sediment. So there's three more depositional landforms that I think you need to know. We've got Polo, and you can see that at Chesil Beach. So this is a spit or a ridge of sediment that connects a mainland to an offshore island. Chesil Beach in Dorset is the perfect example, and that is one of our drift-aligned tombolos. It forms through longshore drift or waves pushing offshore sediments landward. But there can also be a situation where tombolos are created by a swash-aligned approach. If you have an offshore island here and a beach here, then we have the approach of the waves. As it approaches the offshore island, it causes wave refraction to occur. And then we get longshore drift in this direction here like this, and then we get the deposition up here. So it can be drift-aligned or it can be swash-aligned, but your best example in terms of a case study is Chesil Beach. Next up, we have a bar, Slapton Lay. This happens when a spit grows across a bay, joining two headlands together. It traps the water behind it, creating a lagoon. So if you look at Slapton Lay in Devon, the bar has completely cut off the bay from the sea. Next up, we have a cuspate foreland. That's in Dungeness in Kent. This is a triangular-shaped headland created when longshore drift comes from two directions. So where they meet, the sediment is deposited in a series of ridges, and then a salt marsh usually colonises the areas behind, and then we have a stabilised environment. But it's like a very strange triangular shape. And this feature in Dungeness in Kent is so big that it's got its own lighthouse. Next, we move on to subaerial processes. So we spent a lot of time looking at the waves, but the coast is also under attack from the sky. This is when we consider the processes of weathering and mass movement. And these weaken the cliff from the top down, whereas waves obviously attack the base. So if we look at somewhere like West Bay on the Jurassic coast, the vertical cliffs of Bridport Sand are prone to very large rockfall events. The rock is very heavily jointed and it sits on a vertical face. So it doesn't take that much to actually trigger a collapse. The trigger is normally from mechanical weathering. Secret culprit is often freeze-thaw weathering. So rainwater gets into those vertical joints, freezes, expands by 10% and almost like pries the rock apart. Eventually, gravity wins. A massive block detaches and falls vertically to the base, forming a big pile of debris normally known as the talus scree slope. But here's another opportunity to talk about a negative feedback moment. That pile of fallen rocks actually then protects the base of the cliff from the waves, acting like a natural rock armour, if you like, until the sea actually manages to erode the debris away and then we return back to that equilibrium position. And then the cycle starts all over again. So the takeaway? Rockfall is fast, vertical, driven by gravity, and mechanical weathering. Mention the talus scree slope, that's very, very important if we're mentioning how they lead to certain landforms. Next up is St. Oswald's Bay. So don't confuse slumping with landslides. They're two very different things. While slumping rotates, landslides are strict on. And the best example in the UK is St. Oswald's Bay in Dorset. Landslides happen here because the rock layers, or strata, dip steeply toward the sea. They've got a high angle seaward dip. So when you have a flat bedding plane tilted at an angle, it acts like a giant failure plane, if you like, for sliding rock sitting on top of it. So in 2013, after a period of intense rainfall, water worked its way into the joints of the chalk. The water lubricated that contact point between the rock layers, and that reduced the friction. Gravity, again, eventually takes over, and a massive block of cliff simply slid down. That plane of weakness in one go. And so what that creates, a very visible landslide scar on that cliff face, and a big pile of debris at the bottom. So unlike slumping, the top of the land remains relatively stable and in place. It doesn't necessarily tilt backwards. And then finally, we've got Barton-on-Sea. So if you want to see a cliff profile that looks like a giant set of stairs, you need to look at Barton-on-Sea. This isn't just erosion. It's a complex, multi-stage, rotational slump that's created a landscape of what we call benches and terraces. The geology here is what makes this coastline so susceptible to this process. You've got the permeable Barton sands, and they sit on top of the impermeable Barton clay. Rainwater soaks through the sand, but it gets trapped when it hits that clay layer, creating a really high pore water pressure. This lubricates that contact point as it moves along, the water moves along that sand-clay boundary, creating a curved slip plane. As that layer of sand becomes more and more saturated as well, it becomes heavier. So the gravity pulls down on the cliff, and it doesn't fall in one piece, it breaks. And those blocks rotate. So this leaves behind quite a steep scarp, so that's this area here, at the top, and then a series of flat benches just here. So those areas of the land, you'll often see patches of grass, they rotate downwards, and these are our benches. And these things are a nightmare to manage because the movement is driven by water in the cliff. Seawalls at the bottom don't always help. So normally they have to install huge drainage pipes to drain out that excess water to reduce the saturation effect, but also the lubrication effect along those failure planes. So if we're looking at the contribution of any subaerial processes, if you like, to recession, the Holderness coastline is one of our best examples, particularly for rotational slumping. So the reason that it is one of the fastest eroding coastlines within Europe is because this boulder clay is particularly susceptible to that process of rotational slumping. That, in coordination with the fetch across the North Sea, very high energy waves in winter, and you've got a recipe for disaster. So an area known as Skipsea over 30 villages have been lost since Roman times. And this is homes, it's businesses, it's farmland, all disappearing into the North Sea. High energy waves meets low resistant geology. That's where we get our high recession rates. But that focus on subaerial processes is absolutely essential when you are talking about recession rates at the Holderness coast. Right, we then move on to inquiry question 3. Now, inquiry question 3 starts out with sea level change. Sea level change is a complex one because you can talk about both globally driven sea level change, but you can also talk about those local differentiators when we talk about the changes in land level. This is where we have the difference between eustatic sea level rise and isostatic sea level rise. To get the top marks, you've got to be able to distinguish between both of them, but also talk about the nuances of where sea level change might be worse in some places than others by bringing in the combination of eustatic and isostatic factors. So eustatic change, the definition of this is the global change in sea level caused by that increase or decrease in the volume of seawater. 2 main causes. Thermal expansion. This is where the water molecules have been heated, so they have more kinetic energy, so they move further apart from one another. But then we also have the thawing of the cryosphere, which increases the amount of land ice melt, increasing the volume of water in the oceans. Isostatic is more localized. So think of the Earth's crust like a mattress. When you get on your mattress, it sinks like this. So imagine that you yourself are an ice sheet, you go onto your mattress, and it will sink. When you get off your mattress, it will bounce back, and then we have isostatic rebound. They're your isostatic changes. So in the UK, we've got Scotland that's rising previously under the Devensian ice sheet, and then the southeast is sinking to compensate. That's where we get our seesaw effect. Now, we can't only talk about the causes. We've got to talk about the landforms that emerge from this sea level change. So with eustatic change, certainly eustatic rise in sea level, we get what's known as submergent features. Now, the shape that these landforms take depends on the geology, the geological setting, but it also depends on the historical development of physical processes that have taken place within that particular location. First up, we have rias. A ria is a drowned river valley. Think of it as a V-shaped valley that the sea has just moved into. These normally formed in periglacial areas because glacial meltwaters were produced in very high volumes and they carved these deep V-shaped valleys. Then at the same time, sea levels rose because that was land ice making its way back into the ocean store. So what you'll often get with rias is that kind of dendritic pattern. So not only does the lower course get flooded, you also flood the middle courses as well. So these rias end up looking like you can see the branches of the tributaries that have been inundated, I guess. So Kingsbridge Estuary in Devon, perfect example of a ria. Then we have fjords. Now they take on a slightly different shape because fjords form in previously glaciated areas. Sognefjord in Norway is probably one of our best examples here. Now these glaciers are so powerful that they carve these deep, wide, U-shaped valleys. Now you won't get that kind of dendritic drainage pattern that you'll get in rias because what glaciers do is they often truncate any of the spurs that rivers would normally weave their way around. So we get a lot more of a straight profile, if you like, with fjords. Then as the glacier moves down through that valley, remember we've got some terminal moraine that is pushed ever increasingly more towards the oceans and this shallowing sea floor before you get into the fjord. So that's more kind of like what you would see going on underneath the water at these coastlines. But when we actually look at the fjord itself, very steep, high valley sides, and then these wide and deep bodies of water. That forms the fjord, and again we can differentiate it from the rias with the dendritic drainage pattern of the rias and the more straight plan form of the fjords. We've also got the Dalmatian coastline in Croatia. Remember where we had the African and the Eurasian plate converging together? This, in many parts of the world, created these folds, these anticlines and these synclines. Now, the anticlines formed these parallel ridges, these island ridges off the coastline of Croatia. And then the syncline areas became flooded. So when the sea levels rose, the synclines became flooded, and it left behind long linear islands off the coastline of Croatia. So we can also talk about Dalmatian coastlines. Final one is half coasts. Now, what happened with half coasts is, remember, sea levels were 120 meters lower than they were today. That's because a lot of the water was locked up in the cryosphere because precipitation events were snow, fell on land and locked up that water. Then what happened is obviously the glaciers started to melt, and in the outwash plains, they deposited a large amount of sediment. So there's all of this sediment that's now been deposited on this outwash plain. sea levels were around here. Then as sea levels started to rise, constructive waves pushed that sediment back up towards the coastline, where it eventually formed this ridge. And these ridges, these long, thin ridges, were formed along the entire stretches of coastlines, and what's left behind is a haff. It's essentially like an enormous bar, and those lagoons are called haffs. So that's your haff coastline. So there are your 4 landforms of sea level change. And this is a great evaluation point to suggest that is geology really the thing that determines the shape of the landscape? In some locations, we could suggest that sea level rise over longer term timescales has been more important, particularly recently when we've had that eustatic rise in sea level. Next up, we have emergent landforms, and this is because of isostatic change. So while the rest of the world worries about sinking, Scotland has the opposite effect because of isostatic rebound. So when ancient ice sheets vanished, the land began to spring back up, lifting old coastal features high above the high tide zone. So if you look at the Isle of Arran or Fife, you'll see what's called a raised beach. This is a former beach that's now high and out of the tidal range, so often becomes vegetated, and it looks like a flat step in the landscape. We also have features called relic cliffs, and we can see this at Kincraig Point. So behind the raised beach, you'll often find these features because these were features of where wave action did actually attack the cliff. But now, because that cliff has moved back further and further, they are now relics of past marine processes. So these wave-cut notches and caves are now surrounded by grass and trees instead of the waves. But the sea hasn't touched these rocks for thousands of years, and they're not very likely to. So in some parts of Western Scotland, the land is still rising by about 2 millimetres per year, something that's fighting against the current global eustatic sea level rise. Now, we can't just talk about longer-term sea level change trends. We've also got to talk about contemporary sea level change as well. And this is where you have to know the data from the Intergovernmental Panel on Climate Change. Their latest report confirms that sea levels aren't just rising, it's that rise is actually accelerating. So between 1901 and 1971, sea levels were rising at around 1.3 millimetres per year. But between 2006 and 2018, that rate nearly tripled to 3.7 millimetres per year. That acceleration is driven almost entirely by anthropogenic forcing, which is human-induced climate change. So the 2 main culprits stand. Thermal expansion is definitely one, and this is because oceans absorb 90 to 94% of the additional heat that's produced by global warming. And then the second is obviously cryosphere loss. We aren't just losing mountain glaciers anymore. Both the Greenland and the Antarctic ice sheets are melting or thawing to record rates. So by the year 2100, the IPCC still maintains there could be a rise of anywhere between 0.5 and 1.0 meters, depending on our emissions. And there's a number of risks that are associated with this in different economic settings. So what you've got to know for your exam is, how is this impacting developing, emerging, and developing nations? Which is what we're going to come on to now. Now, when we consider developed economic settings, there's no better place to look at than the USA. This is because 40% of the US population lives in coastal counties. In Florida, this problem is also compounded by geology, as the state sits on a porous limestone. This means seawalls can't stop water from coming up beneath the ground. But let's talk money first. It's the US. We've got to talk money. By 2100, over $1 trillion worth of coastal property is at risk. Miami alone, what's called sunny day flooding, caused by high tides, is already forcing the city to spend $400 million on raised roads and industrial pumps. Insurance as well is the silent killer here. As risk rises, premium also then skyrockets. Those insurance premiums are going up and up and up, leading to what's called a coastal mortgage crisis. Socially, the scale is massive as well. An estimated 13 million Americans could be forced to relocate by the end of the century. So while the wealthy can afford to actually raise their homes or move, lower income communities like New Orleans or the Outer Banks face what's called environmental gentrification, where only the rich can afford to stay in these high-risk areas. Environmentally, we see coastal squeeze taking place. So as sea levels rise, salt marshes, mangroves, they try to move inland, but they hit man-made seawalls and highways. So they've got nowhere to go, so they get squeezed. What we're also seeing as well is saltwater intrusion into coastal aquifers, which is ruining the drinking water supply for millions. So to summarize, in developed economies, the risk is mainly to do with high-value assets and infrastructure that's in close proximity to these coastal locations. We can't talk about sea level rise without also talking about Bangladesh, the vulnerable delta. If the US is about protecting property, Bangladesh is about protecting lives and livelihoods. It's a low-lying delta where over 45% of the population live less than 10 meters above sea catastrophe. Let's first look at agriculture and the salinity crisis. Agriculture is the backbone of the Bangladeshi economy, but sea level rise pushes salt water over 100 kilometers inland through the river systems. The salinization ruins the soil. Rice, the staple crop, can't grow in salty earth, so farmers are being forced to switch to shrimp farming, which provides fewer jobs, but also results in environmental damage from the removal of mangroves. The human cost is pretty staggering as well when we consider environmental refugees. The World Bank estimates that by 2050, Bangladesh could have 13 to 19 million environmental refugees. These aren't just people moving for better jobs, they're fleeing land that no longer exists. So most end up in slums in Dhaka, one of the most densely populated places on the earth, putting an impossible strain on the city's infrastructure and services. But remember, what we've also got to consider is that this sea level rise is what we'd call a cyclone multiplier. So it makes storm surges even higher. So even a 1 meter rise in sea level would allow a storm surge to travel much further inland, again impacting more agricultural land and destroying more property. So for Bangladesh, sea level rise is quite simply a threat multiplier. It destroys food security, but also creates that migration crisis. And this is both in the long and the short term with your storm surge event. Now, the best way to consider a developing setting is by looking at SIDS, which are small island developing nations. Within this, we can look at Kiribati and the Maldives. Now, here is where we've got a real existential threat. We've seen the economic hit in the US and the migration crisis in Bangladesh. If the water keeps rising, these nations simply cease to exist. Kiribati is a collection of 33 coral atolls in the Pacific. Because the island is so low, saltwater encroachment is destroying their freshwater lenses. This means that they can't grow their traditional crops like taro. The result? A huge increase in imported goods. So the price of food has skyrocketed, creating a cost of living crisis that is purely driven by climate change. This is why the government has purchased 20 square kilometers of land in Fiji. And this is a policy known as migration with dignity. Okay, so it will allow them to maintain elements of sovereignty, but using another nation state's land. The Maldives is in the Indian Ocean, and it is the lowest country on Earth. The stats here are pretty terrifying. Just a 50 centimeter sea level rise would lead to 77% of the land being lost. So this isn't just about losing beaches. Think about it, it's the Maldives. This is about losing an entire economy, which some suggest 90% of their economy is dependent on tourism and fishing. All of this infrastructure would be destroyed. So one of the ways they're fighting back is by building Mali, which is a new capital, and it's designed to act as this safe haven, if you like. But problem with this is no one wants to move there. So for Kiribati, it's mainly about food security, but also sovereignty. And for the Maldives, it's about land loss and economic survival. But what you've also got to think about is that these small island developing nations, these beaches that are being lost, a lot of the social and cultural activities that take place on a daily basis, the stuff that you don't necessarily read about, is all taking place on these beaches. So they're losing their centers of social and cultural interaction. So there's not just social and economic impact, we can also discuss the cultural impacts as well. So here endeth our sea level rise sermon. Then move on to 2B.8, which is all about causes and impacts of coastal recession. So we start out with the physical, and we can link this back to a lot of the concepts that we've already discussed. So we've got geology, we've got wave action, but we've got other things as well, like the seasons, like the tides, like the fetch, that we can also bring into this formula for why certain coastlines recede at a faster rate than others. First of all, lithology. If your coastline is made of unconsolidated boulder clay, like you are going to recede at a faster rate than if it's made of granite, let's say. So you've got the classic example there of compare Holderness to Land's End. We've also got another factor though, which is the fetch. This is the distance of open water over which the wind blows. Now, the east coast faces the North Sea with a fetch of up to 800 kilometers. This allows the wind to pump huge amounts of energy into those waves. So the longer the fetch, the larger and the more destructive those waves are, and the more intense those processes of hydraulic action and abrasion are going to be, leading to increased recession rates. We've also got tidal range and storms. So a large tidal range, usually when we're talking about your spring tides, when you've got the alignment of the sun and the moon's gravitational attraction, leading to that kind of increase in the tides, a greater volume of water moving through that foreshore zone, so therefore the water has more energy when it hits the cliff at the backshore. If this then coincides with a storm surge, then you have the kind of perfect mix of large volumes of water and therefore large energy transfer from water to backshore to create increased recession rates. So they're your basic physical ones. Now we can also consider human causes of recession as well, so where humans have actually exacerbated the rate at which cliffs will retreat. Now this is normally where we interfere with the coastal sediment cell, and we might starve beaches of their ability to naturally protect cliffs, because if there's a wider beach, there's a greater distance over which the energy can dissipate from waves. So if we create a scenario where we've got a smaller beach, we are going to be directly impacting the rates of recession at that particular coastline. First example, Hull Sands at Devon. So during the 1890s, 650,000 tons of shingle were dredged offshore to build a naval dockyard at Plymouth. Trouble is, these offshore sands were a source of sediment for the authorities thought that the beach would replenish itself naturally. It didn't. The beach level dropped by 6 meters, leaving the village defenseless. And in 1917, a single storm destroyed nearly every single house. So you remove the buffer of the beach, you lose the land. The other example we can look at is the Aswan Dam in Egypt. The Aswan Dam, built in the 1960s, traps 95% of sediment in what's called Lake Nasser. Before the dam, the Nile Delta was built up by the transportation of silts by the river to that particular area of the coastline. But now that supply is cut off. So erosion rates at the delta have jumped from around 20 meters to 200 meters per year in places like Rosetta. So the delta is quite literally starving. And then finally, we've got Mappleton in Holderness. So to save the village of Mappleton and the B1242 link road, they built two enormous rock groins. They trapped the sand. They interfered with the sediment moving through the transfer zone, and this built up a larger and wider beach, which allowed for wave energy to dissipate before it hit the boulder clay cliffs. Worked really well for Mappleton. Trouble is, it caused terminal groin syndrome, which is the result of the starvation of sediment. So sediment wasn't deposited downdrift in Great Cowden. As such, erosion rates in Great Cowden increased to around 4 meters per year. So ultimately, when you're linking human activity to increased recession rates, we're thinking here about sediment starvation and the interference with that coastal sediment cell. Now, we've already talked about a lot of our flooding case studies, if you like, or increases in coastal flooding when we covered our sea level rise. And one of the best examples we can utilize here is Jakarta in Indonesia. This is the sinking megacity. So while most cities worry about sea level rise in millimeters, Jakarta is sinking in centimeters. Today, roughly 40% of Jakarta already lies below sea level. This isn't just a flood risk. For many neighborhoods, inundation is becoming permanent. So what are our causes here? So the primary cause here hasn't been climate change. It all stems from urbanization. So because the city's piped network covers only around 70% of the population, millions of people pump water directly from coastal aquifers. As the water is sucked out, the soft alluvial soils compact because we've reduced that pore water pressure. This is called land subsidence. So in North Jakarta, the ground is sinking at an alarming rate of around 10 to 25 centimeters per year. But it's a double whammy because not only is the land being hollowed out, the massive weight of high-rise construction is physically compacting those younger sediments. So combined with the rising sea level rise in Jakarta is roughly 10 times the global average, with some areas sinking by around 4 meters in the last 40 years. This has involved the ultimate adaptation strategy. So the situation is so dire that the Indonesian government has decided to literally move the capital. So they're building a new city called Nusantara on the island of Borneo because we've essentially reached a point of no return. Another crucial example for your coastal flooding, particularly that short-term coastal flood risk, is Bangladesh and the risk from storm surges. So a storm surge isn't a tsunami. It's a localized rise in sea level caused by a tropical cyclone. So two things happen. Low atmospheric pressure allows the ocean to bulge, if you like. And then because of that low pressure, powerful winds push that bulge towards land. But what's so significant about Bangladesh? Well, we've got the Bay of Bengal, which looks a little bit like this. And it creates a funnel effect. So as the surge moves north into this funnel, the water is squeezed into a narrower and shallower area, forcing it to rise even higher. So add that to the enormous tidal range, and that most of the land is less than 5 meters above sea level, and you've got a recipe for extreme inundation. So let's look at Cyclone Sadir, which occurred in 2007. So it brought a 6-meter high storm surge, which overtopped most of the coastal defenses. It destroyed 1.5 million homes and wiped out the shrimp farming industry in the south. And because the surge traveled so far inland, it contaminated freshwater wells with salt, leading to the secondary crisis of waterborne diseases like cholera. But here's the slight twist, and the slight silver lining, if you like. Deaths from storm surges are actually falling in Bangladesh. So they've built over 2,000 cyclone shelters and have developed a huge volunteer warning system. So in 1970, a similar storm killed around 300,000 people. But in 2007, deaths were around 4,000. So you can see that the resilience in Bangladesh is really improving. So in West Africa, coastlines are receding at about 5 meters per year in places. And this is a social catastrophe. So in countries like Benin, coastal erosion has actually destroyed thousands of houses, but also schools. And because much of the population relies on fishing, this is destroying a lot of coastal livelihoods. So unlike in developed economies, there's no insurance for these families. So when the house falls into the sea, they're left with nothing, leading to forced migration and increased regional instability. But if we flip to the USA, specifically the Gulf and Louisiana, this isn't just about fancy beach houses. It's also about the engine of the US economy. So this region holds 50% of the US oil refining capacity. So sea level rise and storm surges threaten these pipelines and all of this infrastructure that essentially keep the country running through energy. One major storm surge can knock out refineries, leading to an immediate spike in global gas prices because of how much natural gas the US exports globally. So this is a direct hit to not only national energy security, but also international energy security as well. So again, once again, a really useful comparison when we're thinking about the US. Its impact is normally infrastructure property, and now we can also see energy security. In places like Africa, it's usually on subsistence economies and just bog standard survival. Both become devastating in very different ways. Now, we've mentioned environmental refugees a few times, but let's just give ourselves a few statistics, a few AO1 facts that can back up this global environmental refugee crisis. By 2050, the World Bank estimates that up to 200 million people could be displaced by climate change, and a huge proportion of these will be environmental refugees. This is people being forced to abandon their homes because of rising seas, salt-poisoned soil, or disappearing islands. And the projections are pretty staggering. African and South Asian countries are most at risk. And we aren't just talking about a few villages here, we're talking about 1 in every 45 people. So unlike economic migration, this is not a pull to a better life, this is very much a push factor. So take Tuvalu in the South Pacific. Its highest point is only 4.5 meters above sea level. Salt water's already infiltrated the root vegetable pits, destroying its food security, and the government has already signed a landmark deal with Australia, which will allow 280 citizens to locate there every year. A similar deal was also signed with New Zealand, where 75 citizens can also locate there every year. So this is one of the world's first formal climate resettlement agreements. But it's not a choice. It's a managed relocation of an entire culture. In addition to this, we also have the urban strain as well. So where do these migrants go? Well, most move from the coastal locations, which are more rural, to the urban locations, which are more inland. So in Bangladesh, 2,000 people move to Dhaka every day, which has created, we've already said, haven't we, that there's increased strain on infrastructure. But where we've got healthcare and sanitation systems that are pushed to the absolute maximum. So we've had the processes, we've had the risks, we now move on to management. Now, you can't do a coasts management video without talking about Holderness. So managing the Holderness coastline is very much a zero-sum game. So when you use hard engineering to hold the line in one place, you almost always cause sediment starvation in another. So what are our 2 big management case studies along the Holderness coastline that are probably going to be of most use to you in the exams? My recommendations would be learn Mappleton and learn Easington as well. So in 1991, Mappleton was disappearing. To save the village and the B1242 link road, they built 2 massive rock groins. And it worked. Groins trapped the sand, increased the size of the beach, and there was increased energy dissipation. But if we look at the impacts on Great Cowden just down south, because the groins blocked longshore drift, the Great Cowden was not supplied with some sediment, and so recession rates increased to around 4 to 10 metres per year. This is our terminal groin syndrome. Now, this not only destroyed farms, it destroyed a few chalets as well in the Golden Sands Caravan Park. We've also got Easington. Now, Easington's very important. They use rock armour here, and this is because there's a gas terminal, Easington Gas Terminal, which processes around 25% of North Sea gas. So it had to be protected. This is a very expensive piece of infrastructure. So there was the 1 kilometre wall of rock armour to absorb the wave energy that may hit the base. The problem? Well, whenever you put any kind of hard engineering strategy in front of a cliff, what you are essentially doing is you are reducing inputs into the sediment cell system from that cliff. Now, this sediment was a crucial source of sediment for the Humber Estuary and Spurn Point further south. Because we've got less sediment transfer to Spurn Point, that provides less protection for the Humber Estuary. And so what we see is the Humber Estuary shrinking in size, and that is a very important habitat for a lot of bird species. So environmentalists normally kick off because of this. So you can have these two as your perfect example of where hard engineering strategies work and what the positives are, but also where we get those conflicts. Now, next up we have spelt Happisburgh, but pronounced why? Because English. Now, this is along the North Norfolk coastline, and just like Holderness, it is comprised of glacial till, predominantly sands. Now, for decades, this village was protected by wooden revetments. But in the 1990s, the council shifted its policy to no active intervention. Effectively, they decided to let the sea take the land. So, why do nothing? All came down to the cost-benefit analysis and the wider impact on the coastal sediment cell. So first off, protecting Haysborough would cost millions, around 6 million. But the combined value of the farmland and the houses, not just in Haysborough, but along the entire stretch of the coastal sediment cell that would be impacted by the strategies that were put in place at Haysborough, it just didn't stack up in terms of the cost. What would happen, you see, is that if we were to protect Haysborough, Haysborough would effectively become what's called a promontory. Now, a promontory takes place when you have a stretch of coastline, and then maybe there's longshore drift that occurs along that coastline. And if we protect just this stretch here, what would happen is that eventually erosion would take place either side, leaving this kind of jutting out bit here. So what happens then is that longshore drift is then blocked by this promontory, which means sediment starvation further down, which means the loss of land further down drift. So the entire stretch didn't necessarily want to accept this. So they said in Haysborough, sorry, it's a no-go. Sadly, the impact was fairly immediate and fairly devastating. A lot of the homeowners found themselves in negative equity, which means what they bought that property for means that it was significantly lower in terms of the value, and they try to sell it now because who wants to buy a home that's going to end up in the ocean? This is a process known as coastal blight and often leads to a spiral of decline in these locations because it leads to significant amounts of not only out-migration, but a lack of investment in these areas. In addition to this, what it will eventually mean is the sacrifice of some Grade 1 and Grade 2 listed buildings. So there's some cultural impacts associated with this as well. So this led to fairly intense conflict. Locals formed the Coastal Concerns Action Group to lobby the government for any kind of compensation, which currently doesn't exist. They argued that it was quite unfair that their homes would be sacrificed for the greater value of the coastal sediment cell. And fair enough. So Haysborough is a textbook example for both winners and losers for whatever policy decision is chosen. So in your exam, you can use it to discuss the harsh social injustices and that are the kind of harsh realities of economic prioritization with coastal management. Then we come on to some of our more niche examples, if you like. And this is where we're looking at East Head in Chichester, which we'd probably put down as a more adaptive management style. Now, most management plans try to freeze the coast in time, but at East Head, they've realized that's just impossible. The sand dune spit is incredibly dynamic, and over the last 200 years, it's rotated 90 degrees. It's also a triple SI and a vital natural barrier for Chichester Harbour. So the weak point is this area called the hinge around which it rotates. So if the sea breaches that very narrow neck, East Head effectively becomes an island rather than a spit. And this would change the tidal currents in the harbour, threatening multi-million-pound yachts and thousands of homes within the village. So in the past, they used hard engineering, timber groins and like a rock berm hidden under the sands. But today, the National Trust has adopted adaptive management. So instead of building bigger walls, they just decide to work with the sand. So they're utilising beach nourishment, recycling 15,000 cubic metres of sand from the tip of the spit back to the hinge to keep it reinforced. So this is more of a soft engineering strategy that's working with nature rather than against it with the hard engineering strategies. So it's a perfect example of a nice, complex, soft engineering strategy working to protect very high value economic assets. A great idea if you're looking to suggest that without hard engineering, coastal communities could potentially be threatened quite extensively and that soft engineering is not enough. Not always the case. In some place contexts, like in East Head, it is. We've got another example, which is dune stabilization, another soft engineering strategy that tries to work with nature. And the Sefton coast is a really good example of that. So sand dunes, they aren't just tourist attractions, they are vital soft engineering defences. At the Sefton coast at Formby, these act like natural barriers against flooding. But the dunes are actually quite fragile and they can be eroded by one, people walking on them, and two, very high energy storms, particularly from aeolian erosion. The biggest risk here is what's called blowout, which is essentially large windstorms that just take out big chunks of the sand dune. And this actually removes the vegetation, which is what then creates a positive feedback mechanism because we remove the vegetation and that increases the likelihood of further vegetation removal or further sand dune erosion. So if too many of these happen, then the sea can actually flood the areas behind the dunes. So to fight back, managers are using dune stabilization, and one of the key methods here is marram grass replanting. So their roots obviously provide this kind of web that binds the sand dunes together, decreasing the likelihood of blowouts. But they also anchor the dunes in place and allow them to grow higher and higher. In addition to this, they use sand fencing and even old Christmas trees. So these kind of soft barriers are, in addition to marram grass, also things that will increase the likelihood of the deposition of sediment, allowing those areas to build up. And in addition to this, by adding things like boardwalks that provide specific pathways through the dunes, this encourages tourists to stick to these boardways and not go and trample the more fragile areas of the ecosystem. And this allows that Samus-dune plant succession to take place naturally without any human interference. So dune stabilization is a fantastic method because it's cheap, sustainable, and more to the point, protects biodiversity. Okay, next up, we're heading to Lyme Regis for cliff stabilization. So we've seen dune stabilization, now we're looking at cliff stabilization. Now, this is, for me, more of a hybrid between hard engineering and soft. There's a few kind of hard engineering strategies utilized, but it's mainly to stabilize these environments. So there's multiple methods you can discuss within this particular method. Now, the problem with Lyme Regis is it's a bit of a slippery coast. So the problem is in its kind of complex geology, if you like. It's built on a sandwich of limestone, but also unstable lias clay. And because the cliff dips towards the sea, so we've got that high angle seaward dip problem. So the whole town is effectively sliding into the ocean. And since 1900, over 70 houses have been lost to landslip. Now, you can't just build a seawall here. The cliff is effectively moving from the inside. So to fix this, engineers are using what's called soil nailing. So they drove over 1,000 metal spikes up to 20 meters long to effectively pin the unstable surface layers to the solid rock beneath. So it's kind of hard engineering, if you like. Now, remember our rotational slumping example? Water is the enemy. So at Lyme Regis, they've also installed a large number of drainage pipes. So by sucking rainwater out of the cliff before it reaches the clay layers, they reduce the pore water pressure, making the cliff much less likely to slide. Finally, they've protected the toe of the cliff by importing thousands of tons of granite to create a rock armor that reinforces a kind of seawall, if you like. So this acts like a sort of heavy boot at the base of the cliff, providing a physical weight to sort of hold that slump in place and reduce undercutting from wave action. So this program cost around 60 million, and it's a mixture of that hard and soft engineering strategies, like we say. So it's a really good example to bring in, if you're having to debate whether hard engineering or soft engineering is better. Sometimes it's best to just have them work together. It's all context specific, isn't it? Now, every now and again, you do need an example where they've said, we'd love to protect this coastline, but it's just not technically possible. Perfect example for this is under Isle of Wight. So it's the largest urban landslide complex in Northern Europe. But unlike other coastal towns, you won't see any strategies here that are utilized to try and prevent this because it's technically impossible. So the problem is it's the scale of the geological issue here. In Lyme Regis, the landslides are relatively shallow, but here, the slip plane, which is the surface that the land slides on, is incredibly deep. So we're talking about millions of tons of rock moving on a layer of saturated clay that sits way below the reach of any seawall. So to even try to stabilize this, you'd need to re-engineer the entire 12-kilometer stretch of coastline. So the estimates come back at, things like just to re-engineer one road in Undercliff comes back at around 80 million. The cost-benefit analysis just simply doesn't add up because the value of the homes and the infrastructure just don't add up to what it would cost to re-engineer this entire stretch of coastline. So because of this, obviously, the official policy is no active intervention. The council has just had to accept that the land will move, and instead of fighting it, they're just using monitoring techniques. So they have sensors in the ground that warn residents of movement, but as and when the road collapses, it remains collapsed. So the Undercliff is a fairly humbling example of the degree to which we can actually manage coastlines. Sometimes it just isn't possible. Sometimes geology determines your destiny, and it means that doing nothing is the only logical path. Then we move on to Blackwater Estuary in Essex, which is one of your case studies which is very useful for saying that everyone can be a winner. For years, they tried to hold the line at Blackwater Estuary with these expensive earth embankments and some sea walls. But sea levels were rising, the south is sinking, and the walls became far too costly to maintain, not to mention the fact that the farmland that it was protecting was of particularly low value anyway. So in 2002, they tried something pretty radical, which was a managed realignment scheme. Now, this became necessary because what they saw was that in addition to the fact that there was increasing cost associated with the maintenance of these embankments and these seawalls, that they were causing coastal squeeze to take place. So we were losing that natural salt marsh defense anyway. So they intentionally breached the seawall in 5 places. So by letting the sea flood the low-lying land of Abbots Hall Farm, they created 80 hectares of new salt marsh as that salt marsh ecosystem was able to migrate inland. And this is the secret weapon because these salt marshes acted like a massive sponge, absorbing the pressure and reducing the energy on the sea walls. And it's a natural flood defense that naturally grows stronger as sea levels rise. So it's that self-sustaining strategy, making it more economically viable. But we have both environmental winners here and we have economic winners too. So why is everyone a winner? 1, the birds. It created a massive new habitat for Brent geese and redshanks. For the taxpayer, it's much cheaper to create a salt marsh than it is to maintain a seawall. For the neighbours, it's created an area where the flood risk was dramatically reduced by a more sustainable method. The farmer received market value for the land. Tourists can now engage in ecotourism. Through ecotourism, this created local jobs for local people. You see, everyone's a winner. So this project solved the issue of coastal squeeze and it solved the issue of costly maintenance of hard engineering strategies. So it's a sustainable, long-term solution that works with eustatic sea level change rather than against it. So another one of those where we can think about this being a more sustainable strategy rather than those costly hard engineering strategies. Now, you don't want to go into the exam just knowing about coastal strategies in developed areas. Sometimes you've got to think outside the box and you've got to go for some developing and emerging economies. Gazi Bay in Kenya is a brilliant example, and you can bring in all of this synopticity with the carbon cycle as well. So in many developing nations, the best coastal defense is actually not a seawall, it's a forest. So mangroves, their tangled roots trap sediment, prevent erosion, and can reduce wave energy by up to 60%. But in Gazi Bay, these mangroves are not just protecting the land, they're generating income. So this is the first community-led mangrove project to be fully funded by what's called carbon credits. So mangroves are blue carbon powerhouses. So they can store up to 5 times more carbon than terrestrial forests. So by protecting 117 hectares of mangroves, the community prevents thousands of tons of CO2 from entering the atmosphere. And global companies are buying these carbon credits to offset their own emissions. And the money goes directly back to Gazi Bay. And this has funded freshwater wells, school textbooks, and new equipment for local clinics. This gives the community a huge financial incentive to not cut down mangrove forests for whatever economic purpose they might previously have been cut down for, whether it be for timber or for chalk, and to actually maintain them, because there's now a funding stream that comes from the maintenance of these very important ecosystems. So as a sustainable strategy, it's also one of those that you can talk about that has many economic benefits that are appropriate to the economic context. So Gazi Bay shows that coastal management in developing contexts should never be considered cheaper or worse or anything like that. And that actually it can be a little bit more sophisticated and sustainable than in developed contexts. And it's a fantastic example to show the examiner that you can link the carbon cycle and the coast's coastal management strategies and think about coastal management in the 21st century beyond just the traditional strategies of the Holderness coastline. Okay, so your coastal management strategies don't always have to be about mitigation. Sometimes they can be about adaptation, and there's no better community to look to than Bangladesh. In Bangladesh, you're not going to wait around for a seawall that might not come. You adapt your lifestyle to the rhythm of the floods. So this is community-based adaptation strategies. And it's turning one of the world's most vulnerable locations into a masterclass in resilience. So when the land is underwater for around 6 months of the year, you move the farm to the water. And so what they've done in Bangladesh is they've created floating vegetable gardens made from layers of water hyacinth and bamboo. So they rise and fall with the tide and the floods, meaning that even when the land is submerged, food security is still maintained. Furthermore, it's 100% organic, and it is traditional technology that can be effectively scaled up throughout the delta. In addition to this, they've also built in certain architectural designs to help reduce the social impact of storm surge events. So thousands of homes are now built on raised plinths, or these concrete stilts, if you like. So by elevating the living space just 2 meters above the ground, families can stay dry during the storm surge events and the seasonal floods. And they can even use the space underneath for livestock or storage during the dry season. It's simple, it's cheap, and it saves lives every single year. Finally, they're using a bit of biotech resilience. As we saw earlier, sea level rise can poison the soil with salt, but local scientists have now developed a salt-tolerant rice strain, and these crops can now grow in water that would normally kill standard rice. This allows farmers to continue to feed their families, even as that salt front moves further and further inland. So what Bangladesh shows us is that adaptation strategies are not just about big engineering, it's about more localized and more appropriate innovation. So floating farms, raised houses, and salt-resistant crops are the tools of survival. So in your exam, you can refer to this as either grassroots or bottom-up adaptation. And it's often more sustainable than a concrete wall. And that's it. So that takes us through the full scope of AO1 that you could possibly need for the 12th of May exams. So don't forget, if you're keen to go through that final core content overview, the 2-day masterclass is still $14.99. Lock it in while you can. Thank you very much.